Okay, in this video I want to run through the chapter review for kinetics for our class. And in the first question, the question way it's stated, it's a very simple question. I actually want to expand on it just a little bit, talk a little bit more about this particular topic. But when it talks about the average rate expression for not just C, but you can do it for any of the reactants or products in a chemical reaction, it takes on that form of, the rate, and it's actually stated right here, the change in the concentration with respect to the change in time. So let's just specifically address C just to answer the question. Okay, so we're looking at 2 moles of C being produced in this reaction. So the rate of, you could say the rate of the reaction is a function of this equation, if you will, where, the change in C concentration, the change in time, that's a fairly, maybe a little bit more straightforward kind of issue. The bottom line is that once you plug and chug a problem like this, what you would get would be a molarity per second, which is what our rate units are always pretty much for this class. Now, in general, you could talk about any concentration change over time. So just a little heads up for that. It doesn't have to be seconds. It could be minutes, could be hours. You might see atmosphere for the amount up top here. Occasionally, you'll see mole per second, but our textbook doesn't use that very often. And so instead of concentration over time, it's a change in the amount over time. Okay, so anyway, now another aspect of this equation is how to handle the molar coefficient there. And what we say is that whatever molar coefficient is there, we put it as a fraction in this expression. Because basically what we're trying to do is we're trying to compensate for the fast production of C. Like, for example, another aspect of this, if we look at the perspective of if we wanted to follow the average rate from the perspective of the disappearance of B, then it would take on this particular form. Now, one thing that we talked about in class was this idea that, both of these expressions need to equal the same value, the same rate for the reaction. Well, if we just examine the coefficients here in the balanced equation, what we see is that the amount of C that is being produced, it's being produced twice as fast due to that 2 there versus the disappearance of B. And so what these coefficients are doing in here is trying to kind of level the playing field so that, again, the average rate of the reaction can be viewed by, following the change of any of the reactants or products. And then the coefficients here are just there to sort of level the playing field so that really all of these values are going to be equal no matter what we're looking at, no matter what we're following. And then the other aspect is the negative value for the reactants. These are disappearing. So, when you do, right, what does it mean to be delta something? Well, it's always the final minus the initial. For these over here, if you take a data set and plug and chug the final minus initial, you come up with negative values from like this portion of the expression. Well, like I just said, no matter what we're following, we want to have the same average rate for this reaction. So if the calculation of, final minus initial for the reactants produces a negative value, then we need to insert a negative expression, a negative sign at the beginning, just so we get a positive value all the way through. Now, the very last thing I want to talk about with an expression like this is that, if we were given information about the disappearance of B, then we could then predict what the change in C is going to be based on that value. And what you do is you solve for this delta C value here. Delta T, and then equals 2 delta B delta T. And then whether you carry the negative sign or not is less of an issue. The one thing that you always need to remember is that this rate value is always going to be a positive value. So like if you're plugging and chugging an expression like this, and let's say you forgot to bring the negative along for the ride here, if you calculate a negative sign for the value, then what you have to realize is that, that means that sample is just disappearing over time. It just means that you failed to factor in a negative from the formula. Bottom line is, when you calculate the average rate for these types of expressions, or the rate for individual components within the expression, the change is always going to be a positive value. And if you want to look at a specific example of using actually numerical values here, there's a couple examples from the lecture that I would point you to. Okay, so here we are. This is a classic kind of problem that you see in any kind of kinetics chapter, any kind of kinetics test. So, I don't think it's any big surprise if I say that you are going to see a problem like this on the test in some form or manner, maybe a couple of them, because there's a lot going on with a problem like this. Okay, so what do we have? We have an overall reaction. The main thing we want to see from an overall reaction like this is that there's two reactants. The coefficients actually don't play a role in this kind of problem. And also, really, the products don't play a role either. This is sort of a unique data set from section 14.3. And there's always going to be multiple experiments. You're only looking at the initial concentration, of the reactants, and then you're only looking at the initial rate. So that's the change of the how fast the reaction is going at the very beginning of the process, at the very beginning of the reaction. And the first thing you always do for this kind of data set is determine the rate law. So let's remind ourselves what that means. The rate law looks something like this. Okay, so how fast is the reaction going with respect to the concentrations of one or more of the reactants? And so what we do with this kind of data is we figure out what the exponents are for the reactants in the problem. Now, like I said, this coefficient here means nothing. Okay, so there's no correlation between these coefficients and the x's and the y's here. To get the x and y, you have to look at this data here. Let's do that. So the first one that you want to do, or the first one that we're going to do here, let's do A first. Let's see what we need for A. And what you need to find for how A is affecting the speed of the reaction, you need an example where the concentration of A is changing. Usually it's doubling for these problems. You need an example where the other concentration is held constant. So that means that any change in the initial rate is only due to A. Right? So, and what we see here is that I may be doubling the concentration of A, but it has no effect on the initial rate. So basically, this expression doesn't exist in the rate law. And what we say is that it's a zeroth order with respect to A. And one way this can look is, if you raise anything to 0, that equals 1. So the net effect is that it drops out of the expression. Okay, so you're simplifying the rate law with this example here. So sometimes you see zeroth order, first order, second order, maybe third order, maybe 1/2 order, and you figured out all the same way. And what we'll see on B is that there is an order for B. Okay, obviously something has to have an effect on the initial rate of the reaction. And then what do? We do the same thing that we just did. Right? We look for an example where the concentration of B is changing while the concentration of A is held constant. Okay, so that means that any change in the initial rate here is only a function of B. And then you ask yourself the question, well, what is the change that's happening here? Well, if I look at concentration change, what I see is that from experiment 1 to experiment 2, we are increasing the concentration by 3 times. Okay, so that's fine. Essentially what you're doing is you're going to divide the large number by the smaller number for each example. And you do the same thing here for the initial rates. So if I want to see how much the rate is being affected by this tripling of the concentration, well, I just do the same thing. 1.116 divided by 0.124, and that gives me a value of 9. So every time I triple the concentration of B, then I'm getting a times 9 effect on the rate law. And the way this factors in terms of identifying this exponent, well, really what you ask yourself is, what do I need to raise 3 to so it equals 9? And the answer is I need a square. So 3 times 3 is equal to 9. That tells us that my order of the reaction with respect to B is second order. So now I have my rate law. So the answer for A is the rate is equal to K, and it's second order with respect to B. And as a matter of fact, it is second order overall. Right? For an overall rate, you add up all the exponents for the reactants listed. Since there's only one listed, then it's only second order. The same as the order for B. I mentioned a few minutes ago that sometimes the orders are to the 1/2. What would that look like? Okay, so let's just say that we had an example where B is still being times 3, being tripled. The concentration of B is tripled. Well, if it was to the 1/2 order, okay, the 1/2 order with respect to B, what you would see in the initial rate, well, you wouldn't see it increasing by 9. Instead, you would see it increasing by the square root of 3, whatever that is, 1 something. So you would go through this kind of calculation. You see that it's the rate is being increased by whatever the square root of 3 is. Right? So that's like maybe the most complicated kind of example that you may come across on the test here. But again, typically it's 0, 1, 2, maybe 3, occasionally 1/2, but there. Now, what can we do with this? Well, one thing that we can do is that we can figure out what the rate constant is now. So the rate constant, I talked about this in the class. I won't go into great detail here. It's a proportionality constant. Okay, so essentially what it's doing there is I described it as kind of like how hard are you pushing the gas pedal in terms of the reaction for this thing. In a mathematical sense, one thing it's doing is that it's trying to maintain the proper set of units. I mean, we always know that the rate of reaction is amount or concentration over time. And again, for Brown and LeMay, typically it's molarity per second. And if I'm squaring the molarity here, well, I need a set of units so that once I multiply it together, I get, molarity per molarity there, or molarity per second for the rate. And so since this is a second order overall, and the concentration is going to be squared coming from the B square portion of the equation, then that means that the units for K have to be per molarity per second. And the unit for K is going to change for each overall order. It's different from 0th to first order, second order, third order, etc. And we'll actually, so fine, that's the proper units. We'll see that actually in the calculation of the rate constant right now. So let's do that. Now really this is just a plug and chug. I have a rate. I know it's equal to this expression. And it doesn't really matter which one you pick here. In the key, it looks like I picked, let's see, I picked the first one here. Okay, so it's these two data points I'm going to plug into my expression. Right? K doesn't affect the rate. K doesn't show up in the expression, so it's actually not going to be in this calculation. So if I want to calculate the rate constant, I just solve for K here. Now I have values for these two, and I just simply plug them into the formula now. If I evaluate that, I see it is 3.1. And then if I look at all the units here, it comes in with what I said a minute ago. It is per molarity per second. So now I have a value for K. And the 3.1, plus or minus, it could be 3.0, 3.2, that's possible. If you cared out more digits, maybe that's where you'd see the variation. But that value would be the same no matter which experiment you used, no matter which set of data that you used here. And then finally, for C, this is sort of a classic setup as well. You have a new scenario with new concentrations of A and B, and we want to know how fast the reaction is going to go. We have values for all of these terms, and we just simply plug in the new value for B. Right? So in this particular problem, when I set it up, I had to put a concentration of A here because I didn't want you to know that A was 0th order. But the fact is, since A isn't an expression, we don't actually need the concentration of A. Fine. So now it's just a concentration of B, and we have our value for the rate constant. And then what you see with doing this particular exercise is that you see a little bit of how the units work out with the proportionality constant. And that's squared. So if I evaluate this expression, I get a new initial rate for conditions that are not on the listed in the table. Right? And then when I evaluate all the units associated with K and then the square of the molarity, I do come up with molarity per second as expected. And, it's not a bad thing to sort of pause and ask yourself, well, does this make sense? Okay. And it does. Notice how low the concentration is for B compared to all the data points up here. That's what? 3 orders of magnitude. I'm moving the decimal. Right? Instead of this is 10 to the minus 1, this is 10 to the minus 4. It's 1,000 times lower concentration. And as a result, we get a much slower reaction rate. Now, it's going to be, if that's 1,000 times less concentrated and the rate is dependent upon the square, then it's not surprising that we may see, a decrease approaching of a million times slower. So that does make sense. We have a much slower reaction because we have a much lower concentration of B. This particular rate with this particular concentration would be true no matter how high the concentration of A. As long as there's some A in the reaction pot, then this reaction will go at this particular rate at that particular concentration of B. Okay, on number 3 here, we have some chores to do, okay, in terms of calculations, etc. But the first thing to appreciate is what am I looking at? I have a data set of a bunch of different graphs. And when you see a bunch of different graphs like that, what it's really trying to get at is it's section 14.4, the integrated rate laws. And we went through examples of 0th order, 1st order, and 2nd order. And what you're looking for is identifying which one is linear. And then once you've identified which one is linear, that tells you whether it's 1st, 2nd, or 0th order. Okay. Now, I know this one is linear based on 2 reasons. One, I can just simply see this is a pretty straight line. It's being drawn pretty straight through the data points. And then also, I am given an R-square value, right? The closer R-square value is 1, the more linear the sample is. So this is made up data, exactly 1. It's a perfectly linear relationship. This one's not 1. That one's definitely not 1. That's not linear. Now here you can actually identify, say, yeah, that's not linear. The data points are actually going down as a curve, and if you try to set this trend line, it has no fit over top. And you can also see a similar trend here. There's a little bit of an arc to the data points, and that's clearly not a straight line. I mean, it's sort of close, but really, on a relative sense, that's the one that tells us, okay? So, great. The inverse of the concentration of A, the reactant, okay, is linear with respect to time. What does that mean? Well, if you look through your relationships, you find that this is a 2nd order function. And the 2nd order function looks something like this. So from a 2nd order equation here, there's 2 data points. We have K, and K is that value there. It's the slope of the line. And then the other data point, and we don't always use this, but we do use it in this particular problem, is that the inverse of the initial concentration of A is the y-intercept, so 0.0032. So we've actually just answered A, okay, the K is equal to 0.0005. And the units for this, since it's 2nd order reaction, it's the same as what we saw just a second ago. Right? All overall 2nd order reactions will be per molarity per second, just like we saw in that guy. And we did that too. So there's a unit for K. And now we want to calculate the half-life for this reaction. Now the equation for the half-life for a 2nd order reaction looks like this. It's 1 divided by the concentration of the initial concentration of A and K there. Now, one little mathematical trick you can do here is just recognize that you can actually separate these two and do something like that. That's a true statement mathematically. The reason why I mention that is it saves you a step. I mean, if I know the inverse of A naught is that value, then I could just simply plug it in. And then 1 divided by the K value, which is 5 times 10 to the minus 4. And if I then, basically take 0.0032 divided by that value, and I get 6.4 seconds. So what it's saying is that it takes 6.4 seconds for half of the sample of A to react for a reaction like this. So this problem is done. So let me just address some other things you can do with this equation. You can calculate really any aspect of this depending on the data that's given to you for a particular problem. And we saw some of these problems in lecture. And they didn't look like this. They didn't have the graphs there. It would just tell you that the reaction is 2nd order, and it would give you a certain amount of data, and then one thing would be unknown. So, right, if you know that a reaction is 2nd order or 1st order, etc., and you identify the equation that you're going to use, and 3 out of the 4 data points are given to you in the problem, then you're just going to solve for that unknown and then calculate that value. So that's another way that you see these equations being used. And then typically when you see that, you're told what order it is. You don't actually have to go through all of these graphical interpretations. And then finally for our review is an energy diagram for a reaction. So let's go through a quick interpretation of an energy diagram. So transition states are those points on the graph here. They also correspond to the number of elementary steps or elementary reactions here. So each time an elementary step reaction elementary reaction occurs, those reactants have to go through some high energy transition state where bonds are being formed and bonds broken at the same time typically, and that's a process that is high energy. Intermediates are in the troughs, so really it's just B that's the intermediate in this reaction. A reaction being exothermic or endothermic, well, you're just comparing, and that's not a great straight line, but we can see that going from the reactant to the product there is a decrease in their overall energy. So this is an exothermic process. An endothermic process, it would go above the dotted line there. Now, from this information, I can write out a simple overall reaction, okay? And the overall reaction is really simple. I mean, the way this is described, it's A going to C. Elementary steps, or I just mentioned that every time you have a bump, you have an elementary step. And the way to interpret this is that the one reactant, it changes form somehow to form this intermediate B, and then the B has to then get converted over to C. And so what it would look like would be something like this. A going to B for the first elementary step. B is the intermediate, and then it decomposes, changes somehow to then form C. Now, the slow step from any of these reactions is always going to be the one that has the highest activation energy. And so really, you're just looking for, how tall is this one compared to how tall is that one. And you can clearly see the first one is taller, therefore it is the slow step. So if we want to label that, we'd say that is our slow step. And if that is the slow step, well, it's a fairly simple rate law now. The rate would be equal to K and then concentration of A. Let me talk about how we approach this in terms of, relating the elementary steps for reaction to the rate law there. Okay, so one thing to note is that intermediates are never in the rate law. It's always going to be reactants. In this particular example, it's not the most complicated one. You want to look at the lecture notes and videos for the more complicated ones, but it's always going to be a one or more reactants. In this case, it's just one reactant, fine. And since we have no other information, we just have 1 mole of A in that first step. Why do I mention that? Well, when we have the elementary steps written out, this is the only place in this chapter where the molar coefficients actually correspond to the order of the reaction in the rate law. This is the only place you can do this. If it was 2A, then this would be second order, 3A, third order, etc. And then the last thing I want to mention is that when we talk about the rate law, it is dedicated really to describing what's happening at or before the slow step. So what's happening at the slow step? Well, it's just A. So A is the only thing that shows up in our rate law. Again, for more complicated examples, please look at the notes and the videos from lecture. But that's sort of in a nutshell, what information that you can gain out of an energy diagram. And I think with that, we're good.